In this video we're going to be talking about the mole. One thing to keep in mind when we're thinking about chemistry is that with chemistry we view things in the macroscopic world. In reality though, the reactions are occurring at the atomic level. The problem becomes when we try to relate that macroscopic world to the atomic level. So we need some way of relating that atomic or molecular level to something we can actually visibly see or measure in the macroscopic world. So let's take a look at this. Let's say we wanted to count out 1,000 plastic beads, and we knew each bead had an average mass of 1 milligram. So what would be an easy way of counting out these 1,000 plastic beads? Well, it'd take a while to sit down and actually count out 1, 2, 3, 4, all the way up to 1,000. We could do it, it would just take some time. A quicker way of doing it though, because we want 1,000 beads and because we know each bead has an average mass of 1 milligram, we could mass out 1 gram of the beads, and if the average mass of each bead is 1 milligram and we need 1,000 of them, that would give us a total of 1 gram. Now, are we going to get exactly 1,000? Ideally, yes. Reality, we might get a few more, a few less than we actually desire. But that would be a quick way of counting those out. Similar to if we want to get a certain number of molecules or number of atoms to use in a chemical reaction. We wouldn't actually be able to count out individual atoms because they're too small, and we'd have to count out so many of them, it wouldn't be realistic, it'd take too long. Okay, so let's look at another example. Let's say instead of 1,000 beads, you wanted 1,000,000 beads. And well, a million is going to take a lot longer to count out. But let's say we knew that each bead had an average mass of 1 microgram. So how could we measure out 1,000,000 of these plastic beads? Well, it would be equal to 1 gram of the beads. So massing out the 1 gram would be much more preferable than actually counting out 1,000,000 beads. So this is where the concept of the mole comes in though, is this idea of counting out large number of things. So when we're considering the mole, because remember, we're not talking about the animal, the mole, okay? What we're talking about is some way to measure chemical quantities, some way to relate the macroscopic world to the molecular level. And we're going to use a definition that's something called Avogadro's number, that states 1 mole of something is equal to 6.022 times 10 to the 23rd numbers of that thing. All right, so if I had 1 mole of beads, I'd have 6.022 times 10 to the 23rd numbers of beads. If I had 1 mole of bananas, I'd have 6.022 times 10 to the 23rd bananas. If I had 1 mole of cars, I'd have 6.022 times 10 to the 23rd numbers of cars. Okay, you get the idea. This is a conversion unit that allows us to convert between the macroscopic and the molecular level. Similar to saying if you have a dozen of something, you have 12 of those things. Except now we're saying we have 1 mole of something, we have 6.022 times 10 to the 23rd numbers of those things. Another important concept I'm going to mention right now, we'll come back to it. We need to deal with something called molar mass. Molar mass is going to be the mass in grams of 1 mole of a substance. Typically the units are going to be grams per mole. Okay, sometimes represented with gram space, mol minus 1. Okay, anytime you see raised to the minus 1 power, that means it's divided by that unit. So if we know the molar mass, we know the mass of 1 mole of the substance. Well, then we know 1 mole of the substance is going to give us 6.022 times 10 to the 23rd numbers of those things. Right, so that's where that connecting factor is between a mass we can actually measure out in the lab to number of atoms or molecules that are actually going to be used in a chemical reaction. So if we look at 1 mole of carbon-12 atoms, 1 mole of carbon-12 atoms is going to contain 6.022 times 10 to the 23rd carbon-12 atoms. 1 mole of carbon-12 atoms has a mass of 12.00 grams. So if we need to have 6.022 times 10 to the 23rd carbon atoms for a reaction of some sort, we can just mass out 12 grams. Even if we could count atoms, because they're too small for us to see and count, but even if we could do that, it still would take an extremely long time, probably longer than your lifetime, to count out 6.022 times 10 to the 23rd numbers of things. Okay, so we definitely need to use mass. All right, so that's the relationship we're going to be dealing with. You need to keep this in mind. It's a little example of dealing with fixed relative masses. If I have 12 red marbles, and each of those marbles weighs 7 grams, total mass for those 12 marbles is 84 grams. If I have 12 yellow marbles, and each one weighs 4 grams, then total mass for those yellow marbles is 48 grams. The thing you need to keep in mind is that simply because we have the same number of marbles doesn't mean we have the same mass. Same thing's going to apply with a mole. Right? If I have 1 mole of iron, I'd have 55.85 grams of iron. That's 6.022 times 10 to the 23rd atoms of iron. If I have 1 mole of sulfur, that's 32.0 grams of sulfur, and that's 6.022 times 10 to the 23rd atoms of sulfur. Okay, so the number of atoms of each element are the same, the masses are going to be different. So simply because we have 1 mole of 2 compounds or 2 elements doesn't mean those elements are going to have the same mass. We're going to have the same number of atoms, but not the same mass. All right, let's look at this in another example. So each one of those things is going to represent 1 mole of the substance. Inside the balloon, we have 1 mole of oxygen. It would have a mass of 32.00 grams. It would contain 6.022 times 10 to the 23rd oxygen molecules. If I have 1 mole of calcium carbonate, which is chalk, I'd have 100.09 grams of calcium carbonate. I'd have 6.022 times 10 to the 23rd calcium carbonate molecules. If I have 1 mole of water, that's 18.02 grams. I'd have 6.022 times 10 to the 23rd water molecules. If I had 1 mole of copper, I'd have 63.55 grams of copper. And I'd have 6.022 times 10 to the 23rd copper atoms in that. So I think you're getting the relative idea of the mole. Mole is different than mass. We can have the same number of moles but different masses. Okay? So the molar mass in this mole to mass conversion is going to be very important. If we look at a carbon-12 atom is going to contain 6 neutrons and 6 protons. What we've done is we're going to say 1 atom of carbon-12 is 12 AMUs, which is atomic mass units exactly. Now, by definition, 1 AMU is equal to 1.66054 times 10 to the negative 24th grams. You don't need to know that conversion. But the importance of that, it relates then to 1 mole of carbon-12 atoms is going to equal 12.00 grams exactly. All right, but that's only if we have just one isotope, the carbon-12 isotope. But we have carbon-13 in nature as well. So when we look at carbon by itself, just in nature, it could be carbon-12, it could be carbon-13. All right, because most elements occur in nature as a mixture of isotopes, we're going to look at this average. The way we calculate the average, the atomic mass is going to be equal to the sum of the fractional abundance of the isotope times the mass of that particular isotope. When we look at the periodic table and when we look at those masses, remember the mass is under the atomic symbol typically on the periodic table. Those masses are not whole numbers because of those isotopes. So if you look at the molar mass of carbon on a periodic table, it's not 12.00 grams per mole exactly. It's 12.01. Why is it 12.01? Well, because some of the carbon in nature exists as carbon-13. So we've got to use that average atomic mass. All right, so let's look at formulas and see how these formulas are going to help us determine number of atoms, mass of atoms, moles of atoms, moles of molecules, a wide variety of things. So if I look at 1 molecule of H2SO4, sulfuric acid, and I pull up a picture here where atoms of hydrogen are white, atoms of sulfur are yellow, atoms of oxygen are red. Based upon that H2SO4 formula, how many atoms of hydrogen do I have in 1 molecule of H2SO4? Well, I would have 2 hydrogen atoms, right? There's 2 white atoms represented in the picture. Also the subscript, the H2 subscript, that 2 means there's 2 hydrogen atoms. How many sulfur do I have? Well, I have 1 sulfur atom. How many oxygens do I have? I have 4 oxygen atoms. Okay, so in 1 molecule of H2SO4, I have 2 hydrogens, 1 sulfur, 4 oxygen atoms. What happens when I switch to a mole, though? Well, now when I talk about a mole of H2SO4 instead of just a molecule, and you notice my shorthand notation, MOL, we'll use that to represent moles instead of spelling it out all the time as MOLE. It's not much of a shortcut, but it's what we do. So if I look at this, if I want to know the number of moles of hydrogen atoms, and the number of moles of sulfur atoms, and the number of moles of oxygen atoms, I can set up this relationship, where if I start with 1 mole of H2SO4, I want to cancel out moles of H2SO4, so I put those in the bottom in the next step. And I want to convert to moles of hydrogen atoms, so I put moles of hydrogen atoms on the top. And from that formula, I can get for every 1 mole of H2SO4, there will be 2 moles of hydrogen atoms. Now I know this seems kind of silly because you're probably going, well, duh, it's in the formula. We saw that with the molecules. It's still important to make that connection and see this relationship, because these multimole conversions are going to be very important later on, and you need to start recognizing those now. So 1 mole of H2SO4 contains 2 mole of hydrogen atoms. Using that quick math there, number of moles of sulfur atoms, we have 1 mole of sulfur atoms, and we have 4 moles of oxygen atoms. Now let's actually relate this moles then to counting again. So if I had 1 mole of H2SO4, how many atoms of hydrogen, how many atoms of sulfur, how many atoms of oxygen would I have? Well, it's no longer 2 atoms of hydrogens, 1 atom of sulfur, and 4 atoms of oxygen. Remember, we're dealing with a mole, not a molecule. Don't forget, if we're dealing with moles and we want to get to that macroscopic level, like numbers of atoms, we've got to use Avogadro's number. So when setting up the math then, for calculating number of atoms of hydrogen, start with the 1 mole of H2SO4. In the next step on the bottom, we'd put moles of H2SO4 because we want to cancel those units out. We'd put moles of hydrogen atoms on top. In the next step then, we'd put moles of hydrogen atoms on the bottom because we want to cancel those units out. And we'd put the number of hydrogen atoms on top. Okay, so when we plug that into our calculator, we'd get 1.204 times 10 to the 24th hydrogen atoms. So it's not 2 hydrogen atoms, it's 1.204 times 10 to the 24th hydrogen atoms, because we're dealing with a mole of H2SO4, not a molecule. So then the number of atoms of sulfur, using that same sort of conversion setup, we'd end up with 6.022 times 10 to the 23rd sulfur atoms. For the number of atoms of oxygen, we'd end up with 2.409 times 10 to the 24th oxygen atoms. Okay, once again, look at that unit conversion that's being done and pay attention to the units to make sure units are going to cancel out. Okay, so formula weight in molar mass. Well, formula weight we typically use when we're talking about a molecule. When we're talking about formula weight, units are going to be AMUs, which are atomic mass units. So let's look at calculating a formula weight from a formula. Let's go back to the H2SO4. In order to calculate that formula weight, we'd start with 1 molecule of H2SO4, and 1 molecule of H2SO4 would contain 2 atoms of hydrogen. 1 atom of hydrogen then would weigh 1.008 AMUs. Where do we get that number from? Well, that number is from the periodic table. That's the mass under the atomic symbol. Okay, because we're talking about an atom of hydrogen, 1 atom of hydrogen, the units on it are AMUs. So we'd end up with 2.016 AMUs. We could do that for the sulfur. We'd end up with 32.07 AMUs. We could do that for the oxygen, and we'd end up with 64.00 AMUs. So we've calculated the atomic mass for each part of the formula. For the hydrogen, the sulfur, the oxygen. We want it for the entire thing, so all we need to do is add them all together, and we get the 98.09 AMUs. So the formula weight for H2SO4 would be 98.09 AMUs. All right, so just a reminder, when you're looking at the periodic table, don't forget the number underneath this symbol is the atomic mass of that element. If we're talking about a single atom, then the units on it would be AMUs. If we're talking about a mole of that element, units would be grams per mole. So now let's look at calculating molar mass. We're going to use molar mass when we're talking about moles of a substance. And this is going to be more common that we're going to see as opposed to the formula weight, because rarely do we consider just a single molecule. Usually we're talking about moles of something. Units of this are going to be the grams per mole, G divided by MOL, or G MOL to the minus 1. And this molar mass is going to be very, very important. We're going to use it a lot because it's going to connect that measurable macroscopic amount to that molecular counting of the mole. So grams we can measure in the lab, moles is going to deal with the number of atoms and molecules being consumed in a chemical reaction. So the molar mass of H2SO4, sulfuric acid again. Well, we've got 1 mole of sulfuric acid now, and 1 mole of H2SO4 is equal to 2 moles of hydrogen, and 1 mole of hydrogen is equal to 1.008 grams of hydrogen, which will give us 2.016 grams of hydrogen. You notice anything similar between molar mass and formula weights? Really, the calculations are pretty much the same. It's just a matter of which units are we using. If we're talking about moles of a substance, we're using moles and molar mass. If we're talking about a molecule of substance, we're using atomic mass units. All right, so if we do the same for the sulfur the value is the same. If we do the same for the oxygen, the value is the same. We sum them all up, we get that 98.09. And so we end up with 98.09 grams of H2SO4 per mole of H2SO4. And that would be the molar mass.